We would like to take this opportunity to congratulate these young under 40 Innovators Award panel. And well, first of all, congratulations. And I would like to take this opportunity first to introduce every gentleman here. But also, we get into sort of discussions. I'd like to know what inspired them to research certain areas. But what I'm most interested in knowing, and I hope that is also true with the rest of you, is what are the bottlenecks? What problems in the world are you seeing today, and what we can do about it? I'm not asking them to give us answers, but I think it would be interesting to see that any of these, you know, if there are bottlenecks, these are the generation of engineers and researchers who must solve them. All right, so without overdue, let me introduce from to your left. The gentleman is David Atienza, and he is the associate professor at École Polytechnique Fédérale de Lausanne.
You say EPFL is easier.
Yeah, EPFL, okay. Now, so you are a professor, but also you have worked at various companies, and that includes, I have this information that you worked for IBM, Nespresso, really?
Yes, in Switzerland we have Nespresso and Nestle, so these are the two main brands.
And, but also you had a couple of your startups, right?
Yes, we did two startups, one on the area of biomedical, the other one on data center monitoring.
Okay, all right. So your essential contributions to this industry, how do you explain it?
So the main contributions I think come from first the interest of designing new, better systems than what the industry have. So in this part is more on first one on how to manage the energy efficiency of data centers, and the second one is on how to make really these ultra low power processors and so on that you can do today to get this Internet of Things that are going on and very fast.
These are the two hottest areas, right? Yeah. Okay. I'm going to come back to you later, but let's move on. So this is Shen Li, right? Shen Li is a platform architect at Google. You were formerly with Intel Labs, right? And he's been with Google for about a year, I was told. And his contribution include, well, actually, before joining Google, you worked at Intel, but also you worked at HP, is that right?
Right, both Intel research and HP research.
Both research, okay, research job. Now you're at Google, but your contributions to this industry seems to say to model, design, optimize high performance and energy efficient architecture. Am I getting it right?
Right.
Okay. Anything else you'd like to add about that? What are you doing exactly at Google now?
So yeah, I work at Google. Basically, we are working on the next generation of Google's computing infrastructure. That including both the CPU as well as the accelerators, in particular TPUs.
TPUs.
So basically, we understand why we need TPU and how we're going to design TPU, and in connection with the machine learning jobs and models that we use at Google. And then we see how they perform now, and we want to design the new generations and how they perform in future.
Wow. That's what everybody wants to write about and to learn about. Okay, very good. So our third gentleman here, third from your left, is Arijit Raychandri. Is that right? Okay. And he's a professor at Georgia Tech, right? And but he also worked at various companies in the industry. Can you tell me some?
Sure.
Yeah.
Thanks for the introduction. So I am currently in Georgia Tech, but before that I worked for Texas Instruments for about 1.5 years, and then at Intel Labs for around 5.5 years. And in terms of what I think is interesting things that I've done at TI, I worked in the in the world's first integrated DSL modem. So this was a project which was essentially the first DSL modem which had digital analog line drivers on the same chip. So I was fortunate to be a part of the design team that built the first integrated line drivers and eco cancellation units, this was a big success, in the mid 2000s, and it was like the EDN design of the year for a couple of years, and
Wow.
TI that was one of the very successful TI products.
Right.
At Intel, I was in Intel Labs, so I was more in the research areas, and I was working on mostly low power design and resilient designs for SRAM and embedded memory and also logic. These days in Georgia Tech, I keep on working on some of these areas, but I also do a lot of work on computing models and at the interface of math and computing models and hardware architectures, essentially to support these kinds of models. So it's more exploratory at the moment.
At the moment.
Thank you.
Okay, thank you. All right, and next gentleman is, let me see if I'm getting this right. I think, no, I think we'll look at this one. Yu Wang, right? Sorry. And you teach at Tsinghua University. Actually, he came all the way from Beijing for this. And he's also co-founder of DeFi Technology. Can you tell us a little bit about DeFi?
Yeah, actually, DeFi is a deep learning accelerator or deep learning computing platform provider. Yeah, originally we started research from 2012, and then starting the company, raising the money from December 2015, and get the money after 2 months, and then now we have about 150 employees and
Wow.
valued over several $100 million US. Yeah.
Wow.
Yes.
So that's pretty big.
Yeah, pretty big. And and we have Xilinx, Samsung, MediaTek, and Financial, who belongs to the Alibaba. They are our investors.
But your company is based in Beijing, is that
Yeah,
correct?
we are in Beijing. Yeah.
Okay.
all
You
the
have
people-
operations here in the Bay Area, no?
No, people are too expensive here.
Too expensive to live too, right? Yeah. All right. Okay, thanks. So, our last guest there is Zero Zhang.
Yep,
Okay, he is also a professor and he teaches at Cornell.
that's right.
And but he also was a co-founder of AutoESL.
Right, so actually after my PhD, so
Yeah.
so I did a startup, right?
You
So
did the
with my
startup.
advisor, Professor Jason Kong, right? So it's called AutoESL. So it eventually got acquired by Xilinx.
Yeah.
Right? It is a high-level startup.
Yeah, the cheat sheet that I have says that you have been known for the contribution for high-level synthesis for FPGA. Is that correct?
Right, so that's one of the main things I've been working on. So for
You're still
PhD,
doing-
also my
yeah.
startup, right?
Okay, that's your
Okay.
specialty.
Right, because I've been mainly working on raising this design abstraction level, right, for digital hardware design, right? So still current mainstream design methodology is still too low level, right? So this is RTL, right, research transfer level. So we really try to make sure so people don't waste too much time, right? So dealing with low level detail. So if they can actually focus on doing the design creation instead of design implementation by raising design abstraction level to things like high level on time like software programming languages.
But you have never worked for a FPGA company.
Right, so because our startup got acquired by Xilinx, right? So I actually spent a year or so at Xilinx,
Yeah.
right? So sort of helping with the transition of the product.
Yeah.
So that product eventually became Rebottle HOS. Okay, so it's actually being used by many companies and also universities
see.
these days.
All right, very good. All right, we are running out of time, but I'm going to ask each one of you, as I promised in the very beginning, what world's problem are you seeing? What are the bottlenecks that in your specialty or in your area? What are the bottlenecks are you seeing? What needs to be solved?
So, in my view, one of the main processes, we go back to the main topics of DAC
Yeah.
and so on, is the extension from traditional EDA technologies and so on to the system level aspect. So, especially there's this big boom of artificial intelligence, machine learning and so on. So you see there's a very big decoupling between all these huge volume of applications with different aspects and so on, what you can design at the software level, especially very high programming languages and stuff,
Right.
to what you can actually do at the hardware level. There's a very big gap because we still have architectures that are very traditional in that sense. We're
Right.
trying to build accelerators and so on, but still there's a big gap between these two lines. So basically, there's some work trying to really link up these two areas and try to create, but even the programming models and so on, you see they are very different.
Very different.
So I think they are the two communities that are really, really decoupled, and then for the EDA community to really survive, has to go into the upper levels.
Upper levels.
So have to be a full stack design and so on. And I think
Right.
this is one of the main areas where you see, actually most of the work that you have, that we are doing with companies now is on that. So they come for a specific design they have done
Yep.
that doesn't fulfill any of the requirements, and luckily now, which is luckily for me at least, because I like to do hardware and software,
Yeah.
they let you now
That's
touch
it.
everything you want, as long as it actually works.
Right. But how, so there's obviously problems with hardware because the traditional hardware architecture alone would not solve the problems of machine learning or deep learning per se. But what about software? Software is also far behind or still needs to be,
So software has one positive or advantage versus hardware.
yeah,
It's much easier to design. I'm not saying validate, but
Yeah.
verify. But you can build a lot of things that another story if they are secure or safe and so on. So I think there's a very big gap in the software layers at the level of the security.
okay.
So security verifications, you have all these IoT objects that are deployed there. 95% are not secure. I don't think they will be ever secure. Now the point is, what can you do with that? Especially if it goes into sensitive objects
Right.
like cars and so on. So what are you going to do with them?
Yeah.
So I think at the software level is not such a big issue of expressiveness capabilities, but more on the level of guarantees of what you are doing is actually safe,
Safe.
secure, guaranteed, and so on.
Right. That's problems we haven't solved yet.
Yes.
All right. Very good. So tell me what you see as a bottleneck in the line of work you do, research you do.
Sure. So I have been as a platform architect throughout my career, at least so far. And there used to be an abstraction layer that separates the software and the hardware or architecture, and so that both sides can work independent of each other. And that abstraction is actually already starting to collapse.
Oh,
And exactly because of nowadays, we demand ever increasing of the computing power.
right.
We have more data, we have more advanced algorithms, and thus we need more and more computing power. And on the other side, the other world, the Moore's law is starting to slow down by quite a bit. So we couldn't deliver as much as computing power, or at least we couldn't deliver as fast as the increasing rate of the computer power as before. So there is a big gap between the current software and the hardware or architecture. So in my opinion, there won't be a pure software and architecture in future. At least that's what we need to do to solve the problem. So there will be architecture-driven applications or application-aware architectures,
Oh, application aware. Yeah.
architectures,
architecture.
or application-driven architectures, or architecture-aware applications.
Wow.
So we have to have the co-design mindset and to carry on and always.
yeah.
And
So that's actually big change. When you think about PC world, we had a platform, clear hardware roles to play and the operating system, whatever the OS needs to play. But what you're saying is that kind of traditional architecture, software, hardware separation will no longer hold.
right. I think
Will not
that
be there.
yeah.
They won't be there.
It is exactly the type of education that we see more and more in academia. So we don't have any more people that do hardware or do software. So people have to be educated and
Wow.
trained in both ways.
Okay. Interesting. All right. So
So I think this is a good time to be a hardware engineer because I think there are lots of opportunities. For when I joined the industry after I graduated, people were working on different kinds of fixed function accelerators. They were doing all kinds of things. I think the landscape was not very clear. What kind of what kind of workloads need to be accelerated. There was this thought that we need accelerators, fixed function accelerators, but I don't think people were very clear on what kind of workloads, what kind of functionals do need acceleration. Where is the actual hardware bottleneck? I think now we have realized that one of the big applications is machine learning, right? So this is something that's really coming, and we can see this huge difference between even from a GPU perspective, training a very large network takes a lot of time. So if you look at from a design community perspective, what people are looking at, access to higher bandwidth memory, building fixed function units to accelerate some of these workloads. That makes a lot of sense now. So I think there's a lot of stuff which will happen in this domain, I feel.
Right.
The other thing which I think is going to happen, and I can kind of see in all the foundries particularly working on it, is the introduction of high density memory. I think SRAM, DRAM, maybe embedded non-volatile, whatever it is, with high bandwidth. I think that's going to happen. And particularly back end of line memory, like low temperature structures, low temperature memory, low temperature transistors that you can build either 3D stack, monolithic 3D, whatever that might be. But there would be some radical changes there. And as my colleague has mentioned, Moore's law slowing down.
Yeah.
I think there are opportunities. The transistor size may not scale, but I think there are other opportunities in the back end of line that people will try and innovate in. I'm pretty sure that will keep on happening. Yeah. And the other thing I also feel like now that I'm in academia is, you asked about bottlenecks to innovation, right? So these are technical challenges. I think there are smart minds working on it. But the other thing I feel is the semiconductor industry has matured, right? It's been 40 years. There's some sort of maturity going on, which means that we do not necessarily attract the best and the brightest students anymore in our industry. And I think that needs to somehow change as well. I think somehow we need to be able to convince a 19-year-old that what Intel and TIs and Googles and the hardware companies do. I don't think Google has a problem, but I think some of the hardware companies. I think we need to convince them that the rigor, the engineering rigor that goes into building good hardware. There is some beauty to that. I think that's something which is often missed. And I personally, I can feel it these days that we also need to be able to attract the best students for the next decade, so that they can continue innovation.
Going to your point, there was an interesting study in Europe recently that said that Google, Amazon, and so on are starting to be considered as old companies for the teenagers and stuff like that. So I can tell you that in Europe it's not so clear that they are also still innovating.
Right.
As a bottom line.
It's interesting, yeah. All right, so.
Yeah.
What do you see as a bottleneck? Obviously, you are in the also in the thickest of the deep learning platform. So tell me what you see as the bottleneck.
Yeah, actually, I'm not very sure about bottleneck because everybody talk a lot about the merging of the application and the device together because we are in the middle, right? So we are trying to merge them together. And so this is absolutely the trend, and we definitely need something to bridge them, and this is what we can do. So I only see some of the opportunities that what we can do. One thing I think is very important from the deep learning platform builder. You can make one of the machine very efficiently running the deep learning processing. But what about letting multiple machines working together? And what about if you have a lot of resource constraint? So thinking about putting a lot of machines going out together and they work together without a God looking at them, right? And nowadays, people have gods and then they have agents, right? If we take rid of the God, and then how about letting all these kind of small agents working together with all these physical constraints? So there are theoretical models and they have physical real conditions. So how to bridge them? Actually, this is one
So
of the...
this is sort of like in parallel. You are thinking about that the accelerators, not just for one applications, but multiple hardware running
working together for maybe only one application, such as finding someone right in this building, right? So you have multiple agents running inside the building, and how they collaborate together. So a lot of system level, I think, innovation can be done when you have stronger agents.
Right.
And maybe there are some algorithm level innovation and system level innovation and hardware level innovation. You can combine them together. So there is a lot of opportunities here.
Interesting. All right.
All right, so just to follow up what started being said, right, so I'm also actually extremely excited about the process of this so-called specialized
Yeah.
computer systems, right? So where we integrate this, like program accelerators like PGA, GPUs, also some of the domain-specific accelerators like these deep learning accelerators, right? So to some extent, right, so it's already kind of interesting to see that some of the software giants, right, so like Microsoft, right, Google, are building hardware, right, so to sort of differentiate their software, right, service. So I feel like down the road we're actually going to see a whole zoo of different accelerators, right? So we're going to see more interesting applications, right? Probably more compute demanding applications, also more interesting devices, right? So these the boundary between memory and compute are also sort of being fused, right? So we'll see like near memory, right, in-memory compute. So there, like I said, right, so we're going to see a very rich array of different accelerators, right? So that's the part I feel really excited about. I feel like this is sort of the best time to work on these kind of problems. But on the other hand, I feel like it's also sort of most challenging times, right? So because these accelerators are really time-consuming to build. Also, these are really sort of hard, very hard, sort of incredibly hard to program. Okay, so like what so being said before, right? So I actually also agree. So I think this industry is actually losing talent, right? So fewer students coming into the hardware industry, right? So that's where I think we have got to find some leverage, right? So we have to find a way to sort of enable faster design cycle, right? So we have to do the hardware algorithm co-design, but the tools that we have right now are just lacking, right? And also we really need to build more open source solutions, right? So I guess this is one challenge for the audience, right? If you just go to GitHub, right? So, and you just search, right? So machine learning related Git repos, there are like gazillions of them, right? But you type design automation related repos, I don't know, it's probably less than,
Right.
20, okay? So I think these are some of the challenges that we have to, overcome.
Okay. All right. This concludes everything, but if anybody on the floor have any burning questions to the young engineers here, please come to the microphone.
So what are you going to call your startup when you guys all get together and fix this problem?
I think the first question is to see which tasks we assign to each other. That's a little bit of the first one.
I think we are going to call it Innovators over 40.
It's over 40. That's a good one, yeah.
Yeah, or Innovators overload or something like that.
Yeah, in fact, to follow what Ziru just said, he said it's now a very challenging time for the hardware industry. And I think we also feel that it's actually the best time. It's the golden age.
Golden age.
Because we are not the hardware people alone. So we basically open up ourselves to embrace the applications, to embrace the new technologies, emerging applications and emerging technologies. So that's really a golden age for the hardware guys like us.
Yeah, that's a good
All of the audience.
All right, Brian.
What was the most important lesson you learned in the first half of your career that you're going to apply to your second half?
Working with industry, you mean? So if it's related to working with industry, my first learning lesson, and actually still I remember it, in the first meeting was the specs don't matter at all. What matters is what the company really wants and what's the final use case they have in mind. So I remember giving a first presentation when I was really at the very early stage of my career with TI, and actually we were there talking. I showed how good and how great the design we have done, and the manager that was there was getting completely bored. So, and at the end came up and said, so fine, so you get all these benefits, but how do I sell this? We are already having a situation, anyway, my device is having enough performance, I asked you to do this other thing. Have you worked on that? He said, well, I thought it was very boring to work on that. I said, well, that's the only one that I can sell. So you can work on that. Please come back. You cannot work on that, then think of something else. So that was, I think, my most important lesson when I said, the first thing before you start working on something, make a clear spec of what the company wants and why, and then you can actually think about it. Otherwise, another
Clear
thing
objectives, yeah.
I have learned since then, I have been quite successful. So I hope to apply the same thing in the rest of my career, although it's not very clear the specs very often lately. So.
All right, anybody
I
else
agree
wants
with
to take
David.
that?
I think I'll also kind of, now that I'm in academia, I have a little more flexibility in doing what is exploratory research. I think one of the things that I always abide by is something that, and I'll just paraphrase Feynman. He said, something that I cannot build, I do not know. So I believe in that. I think we should be able to build things as engineers. So unless I can build something and I can see it working, I don't believe in it. So sometimes it's hard for hardware, to build silicon. But if you kind of push for it, I think your research will have some impact. That's what I try and do.
All right.
Yeah, actually, for my first 10 years of being a professor in the university, I find out that, okay, I like to play with the students. So this is what I found, because I also got the startup and worked there for about 2 years, trying to gather the money and get all the people around to work inside the company and all these kind of things, which I think the CEO I help with the CEO, which is also my student. So, but after doing that, I find out that I more like to do the 0 to 0.1 is my favorite job. Maybe from 1 to 100 is not my job. So this is what I learned from the first half, I think, yeah.
Okay,
Right.
Yeah, I'll just mention one specific thing, right? So, this is just from my startup experience, also, from my experience building up a sort of brand new research program, right, as a assistant professor at Cornell. So, one specific thing, you have to maintain a positive cash flow, right? So, that's equally important, right, for both industry and academia, right? Yeah, but,
And there are two things I have learned in my past few years. The first thing is to really go to the wild west. It's like we are here in California. It's like the forest blazers, and they came here through the gold rush age, and they came here to conquer the wild. And so just pick the wild west that nobody has ever thought about. Think big, and do not be afraid to fail. And the second one I have learned from all my mentors in the past was that make the trend your friend. So you know the trend and never go against the trend. So, yeah.
Very good. This was one of the most enlightening, actually, panels, because each of you, because of your academia background, very honest in assessing what the bottlenecks is, because you're not in the business of selling certain things that, this does everything. So anyway, thank you so much. Please.
Thank you.
Thank you so much. Thank you.